Session 3 will cover the basic idea behind process behavior charts, the nature of cause and effect relationships, the difference between assignable causes and common causes, the old and new definitions of trouble, the 4 possibilities for any process, and the various ways people use process behavior charts. The material covered in this session will use the Understanding SPC text, where we shall begin on page 2.
So on page 2, in Understanding SPC, you have a diagram. This is a company I worked with. And they were just very typical. You made 100 units, and that got reported to the managers, to the executives, how many units you made. Then you inspected them. Some were scrapped, some were sent for rework. The rework was inspected, some was sent back for more rework, some was scrapped, and some went back to the original inspectors. Eventually, some product escaped and got packed, and they did a quality audit on the outgoing quality on outgoing shipment. So they made 100 units, inspected 166 units, reworked 44 units, scrapped 33 units to get 67 units they could ship. This is what Deming calls the Western approach to quality. Burn the toast and scrape it. Need to improve your quality? Just hire more scrapers. Scrape faster. They actually increase the size of the rework department here at a capital cost of $1 million. And their rework operation was running about $1 million a year operating budget. So their fabrication to shipping ratio, 1.5 to 1. Their inspection to shipping ratio, 2.5 to 1. Rework to shipping ratio, 2/3 to 1. Scrap to shipping ratio, 1/2 to 1. Total burden here, 5 to 1. We are a quality organization. We make everything 5 times. Rothstall came back for a visit in the US. He said, in Germany, I go to talk to people about quality, and their uniform response is, we will put on more inspectors. This is worldwide. Compare that with the reality of lean production for a predictable and capable process. Page 3. Make 100 units, inspect a few for the charts, pack 100 units. So you fabricate 100, you inspect 5 to 10, rework none, scrap none, ship 100 units. So their total burden here is what, 1.1 to 1? Who's going to have the cost advantage in competition here? I told the manager of this department, the manager of this plant, I mean, they said, we don't need SPC. We've got this system going. So this is a way to go out of business. And that's what you're cruising for. 5 years before they went out of business. And when they went out of business, the difference between the red ink and the black ink was less than the operating budget for rework. In the Understanding SPC, page 4, this is summarizing where we've been this morning. Walter Schuhart, working at Bell Labs and working at Western Electric, realized that there was the variation he was used to seeing in the physical world, natural world, and the variation he was seeing in production, and they were not the same. While every process had variation, some processes would display routine variation, while others would display exceptional variation. Page 4 of Understanding SPC. Routine variation is a consistent pattern of variation that is stable and recurring over time. A process with routine variation will be predictable over time. Schuhart's term for routine variation was a bit of an oxymoron to the modern ear, controlled variation. And a lot of people think of control as something you do to avoid variation, so it kind of is jarring. Exceptional variation creates a changing pattern of variation over time. So a process with exceptional variation will behave erratically and unpredictably over time. Schuhart talked about uncontrolled variation here. I'm going to talk about exceptional variation. I think it's clearer. So here is our idealization of a predictable process. Here is a conceptualization of an unpredictable process, which we've seen already today. So at the top of page 6, Schuhart wrote, a phenomenon will be said to be controlled when, through the use of past experience, we can predict, at least within limits, how the phenomenon may be expected to vary in the future. Now, what is the essence of this definition? It's predictability. We could paraphrase this. A process will be said to be predictable when, through the use of past experience, we can describe, at least within limits, how the process will behave in the future. Predictability is the essence of what Schuhart called statistical control. That means that there's two ways to improve a process. When a process displays nothing but routine variation, you can think of the process as being predictable and consistent. And what does Schuhart say about that? This state of control, bottom of page 6, appears to be in general a kind of limit to which we may expect to go economically in finding and removing causes of variability without changing a major portion of the process. Without re-engineering the process, you've reached the limit. On the other hand, page 7, if a process displays exceptional variation, it is changing from time to time. It is both inconsistent and unpredictable. This inconsistency creates excessive variation that has nothing to do with the way the process was intended to operate. Therefore, the first step in improving the behavior of a process, the process outputs, is the identification of the assignable causes of exceptional variation. Notice that these two approaches to process improvement are fundamentally different. One looks for ways to modify a process which is consistent and well-defined, while the other seeks to create a process that is consistent as an identifiable entity. The approach to use depends upon which type of variation is present in the process. This is the first step in any attempt to improve a process. The producer must determine whether or not the process displays exceptional variation. And the tool that Schuhart created for the detection of exceptional variation is the process behavior chart, also known as a control chart. When a process is operating predictably, it's operating up to its full potential. And the only way to improve this sucker, if it's not good enough, is to re-engineer it. But if you've got a process that's operating unpredictably, it's not operating up to its full potential. And trying to re-engineer this is a waste of time. Finding the assignable causes that's keeping it from operating up to its full potential and making them part of a set of control factors, we'll talk about that this afternoon, will improve the process without having to re-engineer it, looking for root causes. So if you got an unpredictable process, root cause analysis makes sense, but reengineering doesn't. If you got a predictable process, looking for root causes makes no sense, but reengineering might be where you have to go. Two different paths to improvement. You need to know which type of variation so you know which approach to take.
Now we consider the nature of data and the difference between assignable causes and common causes of variation.
In the Big Blue textbook, Understanding SPC, let's turn to page 225. We're going to talk about assignable causes and common causes and the nature of the two. Page 225, Understanding SPC. Now, your data are not generated by probability models. They're generated by processes, and processes can vary. Since it is the underlying process that produces the variation, it's helpful to have a model for the structure of the underlying process in order to have some insight into where the variation in your data comes from. Now, let's do a thought experiment here. Think about any product characteristic you might choose, or any operation or transaction that you deal with normally. Now list all of the cause and effect relationships that have an impact upon that characteristic. Normally, people can come up with dozens, if not hundreds, of cause and effect relationships. Now, some of these cause and effect relationships will have large impacts, and some will have small impacts. So if we had perfect knowledge, we could order these cause and effect relationships, and we would probably expect to see something like a Pareto distribution. The critical few that have the lion's share of the impact and the trivial many. So the length of the bar here is the amount of variation in product characteristic number one attributable to each cause. So the causes with large bars are the dominant causes. They will provide the greatest leverage for changing the average value. Causes with small bars provide little opportunity to change the process average. So the producer will typically select the levels of the dominant factors to obtain the desired average level for the product characteristic. Moreover, when the levels for the dominant causes are held constant, these causes will no longer contribute to the variation in the process characteristic. Here, causes 1, 2, 3, and 4 account for 79% of the total variation in the product characteristic, while causes 5 through 21 account for the remaining 21%. By controlling the levels of causes 1, 2, 3, and 4, the producer not only determines the average value for the characteristic, but he also eliminates 79% of the variation in the product characteristic. That's why we like to deal with the dominant cause and effect relationship. The common causes, these trivial many, are the creators of the routine variation in the product stream. So By the choice of our levels for causes 1, 2, 3, and 4, we can shift the process average to a desirable level while reducing the variation of the process. Finally, once the first 4 causes have been controlled, it is unlikely to be economical to attempt to control any further cause and effect relationship. For that, page 228. You see, controlling 1, 2, 3, and 4 reduced the variation by 79% and brought the average to where we wanted it. Now, what if we tried to control causes 1 through 8? Well, first of all, it costs money to control a factor. So it's going to cost you twice as much as controlling 1 through 4, roughly. And you're going to get very little additional leverage for moving the process average. And you're only going to get rid of an additional 9% of the overall process variation. You see the diminishing return that sets in here? Controlling the dominant cause and effect relationships is what you try to achieve. It's what you want to do. We never have enough money. We never have enough time to control all of the cause and effect relationships. So we've got to pick the dominant ones, the critical ones. Economic production requires that we distinguish between those causes with dominant effects and many causes with small effects. Controlling the levels of dominant cause and effect relationships will be economical. Controlling the levels of other cause and effect relationships will not be economical. Causes 5 to 21 make up the set of uncontrolled factors. Now, this is an important point. It is the group of uncontrolled factors that creates virtually all of the variation in the product stream. It's the common causes, what Deming calls them, I haven't given you that language yet. It's those factors 5 to 21 in this example that create the routine variation. So, how does R&D draw their picture? Well, if you try to tell me what R&D, the Pareto looks like this. We don't know. We don't know which factors are the most important. So R&D is set the task of figuring it out. Well, right off the bat, R&D is going to have to do experiments. And you can't do experiments on everything. You don't have enough money, you don't have enough time. So you're going to have to prioritize. So you use theory and experience to identify the 10 most likely factors, the 10 thought to be dominant. And you study those, and then you ignore the rest. Anytime you do an experiment, you make a choice between the factors you study and the factors you do not study. And you're only going to get information about the factors you study. So here at the bottom of page 229, in Understanding SPC, we see the problem. So R&D does the research, and they come up with the following. We studied factors 1 through 10, and we think that you need to control 5 and 1 and 7. And here are the proper levels for 1, here's the proper level for 5, and here's the proper level for 7. So then they throw the process over the wall to production. Have a nice day. So R&D takes their best shot, given the budget they have and the time constraints they have. And they tell you these are important. Now, what they have found is true. So you control 5 and 1 and 7, and you go into production. And you expect what on the screen is yellow. On page 230 of Understanding SPC. But what you get is red. So you go back to R&D and say, is there anything else we ought to be controlling? And they say, oh, you might try 4 or 8, but they're not really very, they don't show very big impact. So you try to control 5, 1, 7, and 4, and you expect the yellow, but you get the red. And so immediately you start talking about the skill it takes to make this product. Words like art and magic are heard. And we settle down to the Western approach, burn the toast and scrape it, make enough toast, some of it scrape out and be good. Because we don't know what's going on. You see, what R&D told us was true, but it was incomplete. Page 231 in Understanding SPC. Factors 14 and 16, which R&D did not study, are dominant cause and effect relationship. So when 14 changes, our process changes. When 16 goes on walkabout, our process goes on walkabout. And it's a mystery. It's magic. And we won't find out about 14 and 16 by studying factors 5, 1, 7, and 4. We've already studied them. We won't find out about 14 and 17 studying factors 1 through 10. What you don't know can hurt you. So the manufacturer doesn't know 14 and 16 are dominant causes, but he's still going to suffer the impact of their changes. When 14 goes south, your process goes south. So we have assignable causes and common causes and control factors. Whenever the set of uncontrolled factors contains a dominant cause and effect relationship, this dominant uncontrolled cause and effect relationship will haunt the process, creating exceptional variation, excess costs, and general grief. Such dominant but uncontrolled causes were called assignable causes by Walter Schuhart. The group of remaining lesser causes were called common causes by Dr. Deming. So here's the story. You've got the factors you're controlling, page 232, and the factors you're not controlling. And in the set of factors you're not controlling, you have assignable causes and common causes. So we have control factors, assignable causes, and common causes. While the levels of the control factors that will determine the average level for the product characteristic, the fact that the levels of the control factors are fixed means they will contribute little or no variation to the product characteristic. Virtually all of the variation in the product characteristic will come from the set of uncontrolled factors. And this is why cause and effect, this is why effort spent trying to fix, fine-tune the control factors will be of meaningless or very marginal benefit as long as there are assignable causes present. You can play with 5, 1, 7, and 4 all you like. It's 14 and 16, they're going to pull your process around. You cannot optimize any system when some of the dominant cause and effect relationships remain unidentified. When the set of uncontrolled factors contains nothing but common causes, we'll have a predictable process. And that's the picture on the next page. If we can take the assignable causes and make them part of the set of control factors, we not only get additional leverage for putting the process average where we want it, but we also take a chunk of variation out of the product stream. Seeking to identify and control common causes will generally prove to be a low payback strategy. All of the dominant causes are contained in the set of control factors. When this happens, you'll have reached the economic limit of finding and removing causes of variation. At this point of economic equilibrium, the product stream will have the greatest degree of uniformity that is consistent with economic production. Controlling additional factors will not be economical. Now, economic operation might not be perfect. You may still have some non-conforming product. If you're not happy with that amount of not 3% rework in this case, then you're going to have to re-engineer the sucker. Now, what happens when you re-engineer? You have new materials, new technology added to the mix. That's additional cause and effect relationships. So you go right back to figure 9.15 with the where the Pareto had all the question marks on it. You're back to stay at step one again. You've got to figure out what's important. I say that here on page 234. When you upgrade or re-engineer a production process, you're changing a set of cause and effect relationships and returning to the starting point. On the other hand, when you identify assignable causes and make them part of the set of control factors, you're simply moving a production process toward the point of economic equilibrium. This distinction between these two completely different approaches to process improvement is a major benefit of having a conceptual model for the nature of data. Since these two ways to improve a process have different objectives, different costs, and different outcomes, it is important to understand how these two approaches fit together. You can operate to full potential. When your set of uncontrolled factors contains one or more assignable causes, it will be economic to identify the assignable cause and make them part of the set of control factors. And this has been done. You'll be operating, gaining leverage. You'll be operating up to full potential. Identifying the assignable causes and making them a part of the set of control factors is simply the only way to operate any process up to its full potential. And this will only happen when observational studies are used to finish up the job begun by R&D. R&D uses an experimental approach. So experimental approaches are very effective at answering specific questions. But experimental approaches are not very useful when you don't know what question to ask. So when you're doing experiments, you've got blinders on. You can only study the factors you know about. You cannot study the factors you don't know about. Process behavior charts are the tool for an observational study. They'll let you listen to the data and let the process tell you about factor 14 and factor 16. And when you find out about 14 and 16 and make them part of the set of control factors, you improve the process. You reduce the variation in the process, and you gain leverage for putting the average where you want it to be. So observational studies complement the experimental approach of R&D. Well, it's important that we meet requirements. Yep, it is. You won't have a customer if you're not meeting requirements. How do you do that? Well, one way a process can fail to meet requirements is by being off target. So what do you have? What leverage do you have to move the average? Your only leverage is the set of control factors. Your only steering mechanism consists of the levels of your control factors. If you have assignable causes, when the assignable cause changes, your process is going to change. And you don't have anything to do with it, except the fact that you're unaware of 14 and 16. So operating on target pretty much requires you to learn how to operate predictably. The other way a process can fail to meet requirements is to have too much variation. Again, if we have assignable causes, they're going to add to the variation in the product stream. But by finding the assignable causes and making part of the control factors, we remove their variation from the product stream. So, observational studies will be needed to complete the process, bringing the upgraded process to full control. While it is important to operate to meet requirements, operating at full potential is a key element in meeting requirements in an economic manner. You see, the only difference between a common cause and an assignable cause is the magnitude of its impact. And when you have a cause and effect relationship that has a dominant impact upon a product characteristic, you're going to find the process to operate unpredictably until you find and remove the effects of that assignable cause. Sometimes you control the assignable cause, sometimes you compensate for it. Either way, you're taking it into account.
Now we come to the 4 possibilities for any process and the uses of process behavior charts.
I was teaching a class, the company that made brake parts. And when you're making brake parts, non-conforming is the dirty word. So they asked me on Monday, and they asked me on Tuesday, and they asked me on Wednesday, how can we be sure we're not going to ship any non-conforming product? I figured I wasn't going to get out of town until I answered the question. So to see how I answered the question, we need to go back in Understanding SPC to page 12, section 1.6. You're going to have 4 things happening before you can be sure you're not shipping any non-conforming product. Your process must be inherently predictable. You've got to operate it predictably. The process average must be at the proper level, and the natural process spread must fit inside the specs. You see, people talk about statistical process control, and to their way of thinking, the word control means inspect. I met people who couldn't figure out what you mean it's out of control. Everything, you've got 100% conforming product. Well, we're talking about 2 different things here. So on page 17, you have a diagram. Looks like this. The old definition of trouble, the one that control addressed, is defined along the product axis. Some non-conforming product produced, you're in trouble. 100% conforming product produced, you're out of trouble. There's your old definition of trouble. and it's understood worldwide. But Shewhart gave us a new definition of trouble. He defined it in terms of the process axis. A process is in trouble when it's operated unpredictably. A process that is operated predictably is operated up to its full potential. It's doing the best it can do, and you can't ask for any more. Now, neither of these definitions tells the whole story, but when you put the two together, you end up with four possibilities. Now, where are you out of trouble? You're in what I call the ideal state. You've got a predictable process, and you've got a 100% conforming product. Process behavior charts got you there. They'll help you maintain process predictability, and they give you a timely warning of any problems with the process or the product. That's where you want to operate. You want to be sure you're not shipping any non-conforming product. You got to be in this state. No other way. Now, if your process is being operated predictably, but you have some non-conforming product because the process is simply not capable of meeting the specs, then you've got product trouble. And here, you're going to have to change the process or change the specs. You might sort, but sorting should be a temporary fix, not a way of life. And process behavior charts will be used to maintain the process predictability and to evaluate your efforts at process improvement. Now, the third of these states I call the brink of chaos, and there you've got process trouble. But the fact that you're shipping 100% conforming product will lull you to sleep. Everything is just fine. But the fact that your process is operating unpredictably means that it's just a matter of time before you're going to be in the state of chaos. And that's double trouble. You got an unpredictable process and you got non-conforming product, and everybody knows they're in trouble when they're here. What are you going to do about it? Assignable causes will dominate. Random fluctuations due to assignable causes will eventually frustrate your efforts at process improvement. The only way out, of course, is to identify and control the assignable causes. The way I got this chart, Charles from the home office went over to the plant and said, okay, you guys need to start using these charts. And they said, we don't know what to chart. He said, oh, come on, bring me the batch weights for last week. So they brought him the log. This is a handwritten log. This is the mix weight X blender in kilograms. This is how much is dumped out of the blender at the end of each mix cycle. It's a pharmaceutical blender. And so here are the weights in kilograms of each batch. So Charles took that week's worth of data and he just started filling out this piece of paper. And he filled out one page and he computed these limits from these data. And these limits tell you this process is not being operated predictably. And so we got the long run below the central line. We got points above the upper limit. Oh, by the way, that upper limit is 1,000 kilograms, a metric ton. That's the target value for each batch. Each batch is supposed to be a metric ton. So these points that are at or near this upper limit are some of the better stuff because all of the trace elements are added on the assumption that you're dealing with 1,000 kilogram batch. So you give me an 800 or 850 kilogram batch, or even a 900 kilogram batch, and your compound is wrong. Your formula is wrong. And the compound isn't going to work right. So the chart tells you they're in trouble, and this is just Monday. Here's Tuesday. He did not revise the limits. He just used the limits from the first page. Here's Wednesday. See the one with an arrow on it? It's clear off the scale. Thursday, early Friday. And by the time they finish up on Friday, looks like they've already been to the pub. So did the process live up to its promise? It told you on Monday it was being operated unpredictably, and it just got worse as the week went on. To page 17 in the Understanding SPC. Processes do not stay put. They move around. And you can see a bit about this as you look at entropy is out there pushing every process down toward the state of chaos. Once you get in the state of chaos, you give a phone call to the local chaos manager. They come out and get in the way of the operators and run some experiments, collect some data, hopefully change things and get you back up here to the brink of chaos. Then they run off to fight some other fire, and the process takes the entropy slide right back down to the state of chaos. You see, most of our improvement efforts are focused on moving from the left to the right because of the old definition of trouble. One engineer told me the following. He said, I work on project teams whose average half-life is 2 weeks, implementing solutions that have an average half-life of 2 weeks. How do you get ahead? So this I call the cycle of despair. And 2 or 3 times around the cycle of despair, it's time to do a process upgrade. We're going to re-engineer the process. Now, what is the rule for process upgrade? Do they deliver everything they promise? Let me make a suggestion. If you cannot operate your current process predictably, you will not operate an upgraded process predictably. I mean, you already know the idiosyncrasies of your current process, and you still are not operating it predictably. Well, a new process, an upgraded process, is going to have new idiosyncrasies, which you won't know anything about. So if you can't operate your current process predictably, I can guarantee that you will not operate an upgraded process predictably. You see, predictable operation is a way of thinking with some tools attached. It's a way of approaching the whole process. And if you don't have that, it's just a blind squirrel looking for nuts. So you get down in the cycle of despair, you're doomed to stay there unless your process is being operated using process behavior charts, because there's a barrier between the bottom tier and the top tier. And that's what the assignable causes are. And the only tool we have to tackle those assignable causes are observational studies using process behavior charts. And that's why processes operated without the benefit of process behavior charts are doomed to operate in the cycle of despair. Well, while we're here on page 18 and page 20, section 1.7, Understanding SPC, page 18, the uses of Schuhart's charts. I list 5 different ways you can use process behavior charts. This is probably not exhaustive, but it covers the ground for most of the ways people use the chart. The first of these uses is the report card chart. We've already seen some of those in understanding variation this morning. Report card charts are charts kept for the files. Management data are often accumulated up to a report card level. And if you put those report card data on a chart, you have a report card chart. Well, there's nothing wrong with a report card chart. It's okay, but you're going to discover that they're terribly insensitive because the accumulation makes them so. We'll look at that several times. In fact, we've looked at it one time already, but we'll look at it several times as we go on. So the secret for using process behavior charts effectively is generally to disaggregate the report card metrics and get closer back to the point in time and space where the actual operations occur. Report card charts, it's often where you start, but if you don't get beyond it, not much happens. The next category, process adjustment charts. I go to various countries, and I got over to Norway, and they said that it's SPC there is statistical process steering when you translate it. And SPC is just the way they think it's a way to maintain the status quo. You have an upset, you get back on track, and then you leave it alone. It's just a manual form of process control. Well, you can use the charts that way, but that's not what they were invented to do. So this is a very weak use, although it's a valid use of the chart. The third category is process trials. You don't see a lot of these because they make wonderful examples. You know what a process trial is. That's when the engineers get in the way of the operators, collect data, and go back to a conference room and argue about it. And they make very process behavior charts, give you a powerful tool to evaluate those process trials. Extended monitoring. This is one step short of doing experiments with a production process, and you usually don't get permission to do experiments with a production process. They've got to meet their production schedule. They got to make good stuff. They're not going to let you just go out there and tinker with it. So you track the inputs, you track the outcomes, and you try to learn from the natural variation in the process about assignable causes, and then you take action to make the assignable causes part of the control factor. An example of that is coming up next. And the fifth category is continual improvement. And the difference between process adjustment and continual improvement is all in the follow-through. The charts look the same. You identify identify there was an upset. In the process adjustment, you just get back on track and let it go. In continual improvement, you say, what is the assignable cause, and what can we do to prevent that from being a problem in the future? So the difference between process adjustment and continual improvement is not in the chart. It's in what you do in response to the chart. We'll see examples of that when we get to chapter 7. Let's look at an extended monitoring example. This was a high volume part, and 50% of the production did not meet the blueprint specifications of 9 mils on the gap. Well, in order to get stuff they could use, there was a deviated spec of 12 mils. Both the producer and the customer got yields 90 to 95% with the 12 mil deviated spec. And this was the status quo for years. The product worked successfully in the field. Everybody knew the blueprint spec was unrealistic. But that was the status quo. You know, quite often specs are what you negotiate, not what you need. Then the automaker decided they wanted to make a quality car. Makes you wonder what they thought they'd been making. So they sent out banners to their suppliers to hang in the plant. We're going to do this quality car by exhortation. The slogan on the banner was, "Whatever it takes." So the customer told the producer, 50% conformance to the blueprint spec is not good enough. We get grilled by the automaker, we're going to be in trouble, and you're going to be in trouble. Well, this is a very profitable business. And the producer did not want to lose it. So he took a project team and put them together and set them to work to find out how to reduce the variation. Over the next 12 months, they actually spent $1 million running a series of 30 experiments. And at the end of the 12-month period, they had 55% conformance to blueprint, up from 50% a year ago. Now the producer is getting desperate. So he sent the whole project team to my class. Now they had been working on this for a year, so their cause and effect diagram already had 600 causes on it. And they couldn't keep 600 charts, they knew it. So they identified 60 they thought were key, and they started plastering the walls of a big room with these 60 charts. And you could track a batch all the way through the process looking at these 60 charts. And over the next 9 months, the 60 charts dwindled down to about a dozen, most of which were being kept online instead of offline. And their cause and effect diagram grew to over 1,300 causes. What was the effect of all this? Well, they found 15 things they needed to change. 12 of these 15 things they had already studied in their set of experiments in the previous year. And 3 of the 15 things were complete surprises revealed by the charts. In other words, they were like factor 14 and 16, surprises, something they didn't know was important, that was important. With those 15 changes, they get 99 to 98% conforming, depending on the part number involved. One of the engineers said, "You know, the charts gave us the courage of our convictions. We're really going to have to fix this, aren't we?" And one of the 3 surprises, they showed me the charts. They came back from a Christmas break, and simultaneously 5 charts jumped outside the limits. And they stayed outside the limits until Thursday, the first week back, and then they all jumped back inside the limits together. Now, when you have 5 charts that are paralleling each other, you've got a pretty strong signal that something's important there. And what they discovered was air dry. The stuff that was outside the limits had been sitting around over the Christmas break, drying out. And they did not have a first in, first out inventory system for the product. They put in a first in, first out inventory system, so everything saw the same amount of air dry time. That's part of the changes, one of the 15 changes they made. So they go to their customer, say, "We can get 98% conformance." The customer said, "Well, we'll help you out. Let's make the spec 13 mils." See, the customer wasn't going to budge until they saw some improvement on the part of the producer. Well, that is the 4 possibilities and the uses of the charts.